Right. This week, we're continuing to talk about the two random variables, especially for the function of two random variables. Last week, we learned that if z, the random variable, is equal to the sum of two independent random variables, then the CDF or the PDF will be the convolution of the two individual PDF x and y. Okay, so we can find the CDF first and then take the derivative. Similarly, um, similarly to next example, so if z equals x times y and x and y are independent, how do I find the PDF of z? And I give you the PDF of x and the PDF of y. So let's see. I want to find the PDF of z. The easier way is that to find the CDF of z and then take the derivative. So to find the CDF, first, what is the CDF of z? By the definition, CDF is a probability. Okay, this is the probability of your random variable z less than or equal to some point, which is z. And in this case, z equals x times y. So x times y less than or equal to z. Now let's see this equation. X times y equals z. How do we plot this equation? So here is x. And then here we have y. X times y equals z. It should be like this. This is xy equals z. And now my x is between 0 and 1. Y is also between 0 and 1. So here it is 1 and 1. So x times y, because x is less than 1, y is also less than 1. So x times y definitely also less than 1. So the area should be here. Okay. So let's see x. X is from 0 to z over y. Here we know this should be the joint PDF, right? But since they are independent, so I can write it down as the multiplication of each PDF. And my x is from minus infinity to z over y. Well, generally, okay, generally because it should be in this area. So from minus infinity to z over y, and y is from minus infinity to infinity. Then I can put f of y outside. Fx dx having the integration. What is this integration? That is the CDF, right? Remember for CDF is the probability, and I can also express, and since the derivative of CDF is PDF, so when I take the integration of the PDF, that's CDF. So I have CDF of x at z over y. Then we can take the derivative of the CDF of z with respect to z. Okay, so the PDF the derivative of the CDF. So let's put the integration here. CDF of a PDF of y times CDF of x at z over y dy. We have z here. So let's have a chain rule. A chain rule means here I have a PDF of y and df x, here is z over y. So we have dz over y. And then we have dz over y over dy. So we have integration PDF of y times, that is the PDF of x at z over y, right? Times 1 over y dy. Now we don't need to think about the upper bound and the lower bound. Here we know x is between 0 and 1. And we know x is z over y. Therefore, z is less than y. And also we know y is less than 1. That's from the question, the problem. Y is between 0 and 1. Hence, y is between z and 1. So the y is between z and 1 over y squared dy. So we have 2 times 1 minus z. And z is greater than or equal to 0. How about z less than 0? Z less than 0, the PDF is 0. So we found the PDF of z. That's 2 times 1 minus z, and then the z is greater than 0. All right, so this is a case for x times y. We have learned x plus y, x times y. How about the subtraction? X minus y. Let's take a look. Still, x and y are independent, and z equals x minus y. Let's find the PDF of z. Again, we can find the CDF of z first, and then take the derivative. So the CDF of z is the probability. The probability z less than some point here, we have z. And we know that z is x minus y, so here we just replace z by x minus y. So x minus y is less than a certain point, z. Okay, let's plot z minus y equals z, this equation. Here's x, and here's y. Okay, this is x minus y equals z. So here should be minus z, and this is z. Now, x minus y less than z. This part or this part. The easier way is that since you have a line, then we can check it by the origin. So let's put origin inside. We want x minus y equal x minus y less than or equal to z. So let's check 0, 0. So 0, 0 is less than z. So the area is this part. So the area is here. So let's check for x. X is from minus t, from minus infinity to z plus y. Okay. So the x, again, we have the joint PDF, but since they are independent, so I can write down the multiplication of their individual or marginal PDF. So we have f of x times f of y dx dy. My x is from minus infinity to z plus y, and y is from minus infinity to infinity. Then we have the PDF of y times integrate the PDF of x. And we have the CDF of x at z plus y. Then you can take the derivative to get your PDF of z. So df z dz You can also do the chain rule, so you'll get PDF of y times PDF of x at z plus y. And now the y, where's the y? Y, we have values less than 0. So that will be from minus z to infinity, but since I don't have values after 0 greater than 0, so my y is from z minus z to 0. Okay, so here we have from minus z to 0 e to the y e to the minus y plus z dy. So again, we can check x is greater than 0. So y plus z is greater than or equal to 0. And we also need y less than 0. So overall, minus z less than y and less than 0. And here is minus z to 0 times e to the minus z dy. You get z times e to the minus z. Therefore, your f of z, the PDF, is either z times e to the minus z when z is greater than or equal to 0, or it is just 0. So we have seen z equals x plus y, x times y, x minus y. You can also try it by yourself, like x divided by y. But here, let's see another different function called z equals the maxima of xy. So it is either x or y. And in this case, you see that x and y are not independent, or we don't know because we didn't tell you the information. You just have the joined PDF. For this joined PDF, I want to find the PDF of z. Z equals either x or y. We choose the maximum value. How do we find the PDF? No matter what functions you have, to find the PDF, two ways. First, you can find the CDF and then take the derivative of your CDF, you get the PDF. Or you can use the direct method to find the PDF. So here, we can also think about the CDF first and then take the derivative. So what is the CDF of z? That is the probability of random variable z less than or equal to some point. Here we just say z. And we know that z is the maximum value of xy. Then how do we plot this function? Maxima xy equals z. X and y. If I have a z here, so the maxima xy less than or equal to z is either x or y. And then either this x or y that's less than z. Oh, and also the PDF, well, first, x is less than y. Right, so suppose I will choose the maxima, and from here, we should know that x is less than y. Then the maximum value should be y. So y is less than z. I should have this area. So this means y is less than z. Then you have e to the minus y dx dy. Your x is from 0 to y, and your y is from 0 to z. So you get 0 to z, y times e to the minus y dy. Then your PDF of z is taking the derivative of your CDF of z. dz. Now you have d over dz 0 to z, integration from 0 to z, y times e to the minus y dy. Okay, so here we will use the fundamental theory of calculus. So let's see what is the fundamental theory. The fundamental theory of calculus. How can I get the function of f of x? You can take the derivative of the integration so we apply that to here. We'll get z e to the minus z. So your PDF is either z times e to the minus z when z is greater than or equal to 0. Otherwise, it is 0. Next, x is a random variable, and I have a PDF of x. And now y is a function of x. Now, well, we want to find another random variable, z. And z is x minus y. And what is the expectation of z squared? Looks like we have three random variables. One, the base one, random variable, and y is a function of x. And z is also a function of two random variables. Then what is the expectation? First, we want to find the expectation of z squared, like the second moment. How do we find the second moment of z? Still by the definition. Okay, what is the definition of the expectation? Consider all possible function of outcomes, that's z squared. And since this is random variable z, so the corresponding weighting is the PDF of z. So no matter what z is, this is general term, the always satisfied. But in real life, sometimes it is really hard to find the PDF of z. So here, how to figure out or how to find or how to even calculate the PDF of z. So we cannot find this expectation directly, just using the z, the information of z. Therefore, we need to find another way. we know z is x minus y. So it should be x minus y, and y is g of x. We know PDF of x, so it's good. Here, by the linearity, we have expectation of x squared minus 2 times the expectation of x times g of x, and then plus the expectation of g squared. So for x squared, we know the PDF of x. So consider all function of possible outcomes times their corresponding weightings, then have f of x. And then the middle term, also consider all possible function of outcomes. Here we have x times g of x. And then their corresponding weighting, it is still the PDF of x. The last term, a function of a random variable. So consider all the function of outcome, a possible function of outcomes times their corresponding weighting, which is still f of x. Now you can find the expectation because these are all known. So now let's see some notes for the expectation here. X times g of x, they are all x. So the expectation is to consider all possible function of outcomes. So x times g of x, their corresponding weighting. Here the corresponding weighting is PDF of x. Or maybe this time it should get green. Let's see the second one, x times g of y. I have two random variables, so the expectation, I'll consider all, that's r squared. Possible function of outcomes, here I have x times g of y. And then their corresponding weighting, what is their corresponding weighting? Which PDF? Since I have x, y, so I should have a joint PDF. Dx, dy. Then if I want to find the expectation of x times y times z, three random variables, so I consider all will be in the space R3, x, y, z, and then their corresponding weighting, their joint PDF x, y, z. Okay, next, the expectation of x given y equals a certain value, that the expectation is consider all possible outcomes. The possible outcome is x. Now the question here, what is the corresponding weighting for this expectation? It is conditional PDF, conditional random variable. So I have conditional PDF, x given y, dx. Remember that after taking the integration, your results should be a function of y, and y is fixed. The last one, if it is x times z given y, still conditional PDF, a conditional random variable. Here, the expectation, because I have x and z, so there will be like two random variables. So I will consider O, that will be in R squared. X times Z. The corresponding weighting here, what kind of PDF do we have? The conditional PDF, and this conditional PDF is XZ given Y. XZ given Y. Here dx dz. So at the end, there will be also a function of y. Okay, and so here we have a summary of the sum of two independent random variables. If x and y are independent, then and also z equals x plus y, the PDF of z will be the convolution of the PDF of x and PDF of y. So PDF of x convolve PDF of y. So this is the convolution. Okay, so that is the function of two random variables. Here, let's see the next topic. We want to know what is moment generating function. And here is the definition. For the moment generating function, x is a random variable. Then the moment generating function is this one. The expectation of e to the sx. And this s is a parameter. So in discrete case, there will be the summation. In continuous case, I do the integration. Okay, because it is the expectation. So since it is an expectation, I consider all possible function of outcomes times their corresponding weightings. Here, for discrete case, it is the PMF, which is a probability. For continuous case, we have the PDF. And if you see this integration, a function times e to the sx, you may see that actually the moment generating function is a Laplace transform of the PDF. So if we let s equals minus jw, j omega. So if this is minus j omega times x, now the moment generating function at minus j omega, that is the Fourier transform of the PDF. So now, for example, the generating function, moment generating function of a Poisson random variable. Okay, this is the definition. And here we need all possible outcomes, function of outcomes, and then the PMF, the corresponding weighting PMF. Since it is Poisson, so here is the PMF. And then we have exponential term. Also, we have the exponent. They are all x, so we can combine it. Let's combine this. X is from 0 to infinity. Lambda e to the s over O to the component x times e to the minus lambda divided by x factorial. Remember, x from 0 to infinity, x to the k divided by k factorial. That is the exponential to the x. So therefore, this one, if I take the e to the lambda outside, because we do the summation with respect to x, so this part, k factorial, something to the k, then I have exponential groups. E to the lambda, e to the s, times e to the minus lambda. Let's see the continuous case. what is the moment generating function of exponential random variable? So again, that by the definition, consider all possible function of outcomes times the corresponding weightings, that is the PDF of x. Now we can bring in the PDF of exponential random variable. That is from 0 to infinity, e to the sx lambda times e to the minus lambda x dx. So it's lambda times e to the s minus lambda x dx. So which is lambda over lambda minus s. If the lambda is less than s, greater than s. Okay, now let's continue to see the properties of the general moment generating function. So if first x and y are independent and z equals x plus y, then what is the moment generating function of z? So the moment generating function of z will be the multiplication of the moment generating function of x and y. Because the moment generating function of z, by the definition, is the expectation of e to the s z, a function of random variable z. And we know that z is equal to x plus y. So here e to the s x plus y. And since x and y are independent, I have e to the s x times e to the s y. They are independent, then I can separate these two expectations. And that is the moment generating function of x and the moment generating function of y. So this is just for x and y, they are independent. Suppose I have xi and they are all independent. So I have a summation, the x z equals x1 plus x2 till xn. Then the moment generating function will be expectation e to the s x1 plus x2 plus x3 to xn. Similarly, I can get expectation of e to the s1, expectation of e to the x2, expectation of e to the x3. So it is the multiplication from 1 to capital N e to the, expectation e to the s xi. Here we just say that x1, x2 to xn are independent. Now suppose if the xi, they are IID, identical independent distribution, or IID, then the moment generating function of z is, they will be the same. Okay, So I do this n times. So this is a moment generating function of, say, x1. We do it n times. So here I have like moment generating function of x. You just randomly pick one, say x in, right, of s, and then I do it n times. Next, the moment generating function at 0 is 1. And if I take the derivative k times, take the kth derivative, and set s equal to 0, we will get the moment, kth moment of x. So here we can prove that the moment generating function at 0 means this is the expectation e to the 0 times x. Okay, so because s is 0, so this is the expectation of 1, a constant, so here is 1. Now let's take kth derivative of this moment generating function. So dk over ds k. Because this is the expectation. Okay, so I have considered all possible outcomes times the corresponding weightings, so I have an integration. So I have integration, consider all, and we'll put the derivative inside the integrand. So inside the integral, I have the weighting dx. So I do that k times kth derivative. I have the integration from minus infinity to infinity x to the k times e to the s times the PDF of x. So now we can set s equal to 0. That'll be, so s will be 0. We have s goes to 0, this is 1. So I have x to the k times the PDF So what is this integration? Again, you can think about this integration as consider all possible function of outcomes times the weightings. So that's the expectation. Expectation of x to the k. That's kth moment of the random variable x. Okay, so now knowing the moment generating function, we can explain like why the sum of the IID Bernoulli random variable will be equal to the binomial random variable. So I have an IID Bernoulli random variable. And then if I sum of these random variables, then actually this is a binomial. So I consider the sequence of the IID Bernoulli random variable. We call xn. And then the Bernoulli random variable with the parameter p. And with that, another random variable z equals sum of them. Let's find the moment generating function of z first. By the definition, that's the expectation of e to the s z. This is a function over a random variable. And we know that z, because we don't know the distribution of z. That's hard to find the expectation directly. So we need to figure out another way. And since my z is the sum of n Bernoulli random variable, so here we can change that to x. And since they are independent and also identical, so that is the product of your expectation e to the s xn. And we know for the Bernoulli random variable, the moment generating function, later on you will have a table. It is the parameter p times e to the s plus 1 minus p. And we do it n times. So finally, that is this term to the power n. And now let's check the moment generating function of a binomial random variable. So now can check the moment generating function of a binomial random variable. So if the random variable z is binomial, and then the parameter is n, capital N and p, let's find the moment generating function. We always do it from the definition. So that's the expectation of the function of a random variable. And since now we know this is a binomial, so we can get their corresponding weighting. Their corresponding weighting is binomial PMF. So it should be n choose k, p to the k, and 1 minus p to the n capital M minus k. So this is k from 0 to capital N. So n choose k. For this summation, there will be p times e to the s to the power k times 1 minus p to capital M minus k. And this is p to the times e to the s plus 1 minus p, and overall to the power n. How come? Remember, a plus b to the capital N. That means the summation k from 0 to capital N, and n choose k. Here I have a to the k power times b to the power m minus k. If x and y are independent and x is Bernoulli, y is exponential, and I want to find the moment generating function of z. The z is 4 times xy. How do we find this? To find the moment generating function of z, then we just write it down the definition. The moment generating function of z is the expectation of e to the sz. Well, consider all possible function of outcomes times their corresponding weightings, but we don't have any information about the PDF of a z or even PMF of a z. So we need to find another way to replace z, because we have an equation z equals 4xy. Here we have e to the s 4 times xy. Then we can use total probability law. We can fix one here, because y is continuous and then x is discrete, and x is Bernoulli. Bernoulli means x is either 1 or 0, right? So either 1 or 0, that's easier to analyze. So we can fix x, say first x equals 0, and then we consider x equals 1. So I can fix we fixed x equals 0. Since we fixed that, we also need to times the PMF of x at 0. And now the second one that I also need to consider the 1. So I also fix x equals 1. So I have expectation e to the 0 times 1 minus p. And then expectation e to the sy times p. So we have 1 minus p. And then here we have the moment generating function of the exponential random variable times p. So the moment generating function for the exponential random variable will be lambda divided by lambda minus 4s times p. This is one way to find that. And since x and y are, one of them are discrete and the other one is continuous, we can also think about this expectation using the definition. And also x and y are independent. So here, another way to find the expectation e to the s times 4xy could be, since they are independent, so for y, consider all possible outcomes, O is from 0 to infinity. And for x Bernoulli, so consider O, x should be either 0 or 1. Possible function of outcomes, e to the s 4xy. And then the PMF of x and times the PDF of y. So here, so that's why here you can see that x is either 0 or 1. So when x is, so here I have x equals 0 plus x equals 1. So I have two terms. So the first term, if x is 0, I have a px, the PMF of x at 0. And since it is 0, so the exponent, this exponential is 1 times lambda e to the minus lambda y dy. And when x equals 1, e to the 4s y lambda times e to the minus lambda y dy. That's why here. So we have 1 minus p plus the PMF of x at 1 times the expectation of e to the s for y. Now let's see next example. X random variable with the moment generating function. Now I want to find the variance. So I only have a moment generating function. Then I want to find the variance. Remember that the moment generating function is the expectation. So we can directly find the variance because variance is the second moment minus the first moment square. So we need to find the second moment and the mean. So the variance of x is the second moment minus the first moment squared. How do I find the first moment, which is the expectation or the mean? Remember, we have the property. We can take the derivative of the moment generating function because it is the first moment, so we just take one derivative and then set s equals 0. So we have 20 times 1 divided by 1 minus 5s to the power 5, and then set s equals 0. Then you get 20. Now to find the second moment, so we need to take the derivative twice. D squared over ds squared, and then later on set s equals 0. So we will take the derivative from the previous result. So here I have a ds and then d20 divided by 1 minus 5s to the 5, and then set s equals 0. Then you'll get 500 divided by 1 minus 5s to the power 6. And then set s equals 0. So we get 500. So your variance is 500 minus 50 squared, 20 squared. So we got 100. That is the moment generating function. Another function is called characteristic function. Remember that if I set the s to minus j omega, it becomes the Fourier transform. So let's just do it. We restrict the s to the imaginary axis, s equals minus j omega. So the moment generating function becomes a characteristic function. So here's the definition of the characteristic function. There'll be e to the minus j omega x. So see, this is the Fourier transform. So the expectation e to the minus j omega x is the Fourier transform of x. Hence, e to the j omega x, I take the expectation, there will be the inverse Fourier transform. And in most of the textbook, actually, you will see the the characteristic function as the definition is this one. e to the j omega x rather than e to the minus j omega x. Okay, but in our class, we just define the characteristic function is the Fourier transform. Okay, it'll be easier to check the table. Okay, because since we know that this is a Fourier transform, then we can see the table to find the characteristic function. So, for example, x and y are independent. I have a PDF of x and then the PDF of y. Then I want to find the PDF of z. Z is x plus y. How do we find the PDF of z? In the past, we say to find the PDF of z, two ways. Find the CDF of z first, and then take the derivative to get the PDF. Or you have the direct method to find the PDF. Now, since we talked about the characteristic function, that is the Fourier transform of your PDF. Okay, this is the Fourier transform of your PDF. So that means to find the PDF, we can find the characteristic function. Once we have the characteristic function, then I take the inverse Fourier transform, then I will get the PDF. Right? So let's see, to find the characteristic function first for this question. I have a PDF of x, so the characteristic function of x is, we can also just check the table, and in the exam you also have the table. It is lambda divided by lambda plus j omega. And the characteristic function of y, that's lambda divided by lambda plus j omega. So how about the characteristic function of z? Because characteristic function of z is the Fourier transform of the PDF of z. Expectation e to the minus j omega z. And we know z, since we need to find the PDF of z, so I cannot just take directly the PDF of z here, because we don't know. That's what we want to find. But we know z equals x plus y, so we can replace z into x plus y. Since they are independent, so we have e to the minus j omega x times expectation e to the minus j omega y. This is the characteristic function of x, characteristic function of y, right? So it should be lambda squared divided by lambda plus j omega squared. So we can take the inverse Fourier transform or see the table. We can find the PDF of z. So taking the inverse Fourier transform, we have the PDF of z. It'll be the inverse Fourier transform. Lambda squared divided by lambda plus j omega squared. That's equal to lambda squared times z times e to the minus lambda z. Z is greater than or equal to 0. Remember that we also learned that this week and last week. If x and y are independent and I have another random variable z that's equal to the sum of these two independent random variables, the PDF z, what is the PDF z? We can do the convolution. The PDF of x convert PDF of y. That is also one option, but you can see that doing the convolution is really complicated. So we can use a characteristic function approach to find the PDF. Okay, so this is simpler, much simpler than the convolution approach. Then you may ask, well, seems you use the Fourier transform and inverse Fourier transform to find the PDF. But how about the moment generating function? Moment generating function, this is just Sx. And then here, I still have a PDF. So I can also find the inverse inverse Laplace transform to get the PDF, right? So why the characteristic function, not the moment generating function to find the PDF? We know that actually for the moment generating function, the Laplace transform is not always defined, but the Fourier transform is always defined. So that's the reason. The moment generating function is not always defined. Since we said that the Laplace transform is not always defined, here let's see. If I have a Cauchy distribution, we have a PDF like this. Let's find the moment generating function, which is let's find the Laplace transform. Okay, so moment generating function e to the sx times the weighting pi x squared plus 1 dx. Now, the integration is from minus infinity to infinity. So it is definitely greater than or equal to the integration from 1 to infinity. And this is greater than or equal to sx cubed divided by 6 pi x squared plus 1 dx, because e to the sx is greater than or equal to sx cubed divided by 6. That is, so this term is still greater than or equal to the integration 1 to infinity. Here I have sx cubed divided by 6 pi 2x squared dx. And this is s cubed divided by 12 pi. And you'll see that this integration is to infinity. There's no Laplace transform, so there's no moment generating function. But if I take the Fourier transform, by the Fourier transform, the Cauchy distribution here, 1 divided by pi times x squared plus 1. That is the exponential minus the square root of omega. Okay, now let's see the useful property of the characteristic function. X is a random variable, and we know the characteristic function. Now, y is a function of x. It's a line, ax plus b. Then, the characteristic function can be expressed as the characteristic function of x times e to the minus j omega b. If you think about the Fourier transform, you can see that this is scaling and the shift. No wonder I think that where's the scaling part? It should be j a omega. This is a shift part and then a scaling part. So quickly prove this. The characteristic function of y, always from the definition, that's expectation e to the minus j omega y, a function of y. And since we don't know the PDF of y, but we know the relationships between x and y, so here we have e to the minus j omega, and y will become ax plus b. And that is the expectation of e to the minus j omega ax plus, times e to the minus j omega b. There's no, this is a constant, so I can put it outside. So e to the minus j omega b, and the expectation e to the minus j a omega x. So now omega becomes a omega. So this is the Fourier transform. Oh, no, this is the characteristic function. Okay. J and omega becomes a omega. Now let's see the moment theory. So what is the moment theory? For the characteristic function, the nth moment of the random variable x is in this way. So this is nth moment. Okay, nth moment is always the expectation to the random variable x to the nth power. So I take nth derivative of the characteristic function and then set up j omega equal to 0. That is your nth moment. Okay. So if I have a Laplace PDF, so it should be f, not CDF. Okay. So f over x, it's alpha to over 2. Well, this is just Laplace PDF. I want to find the characteristic function, mean, and the variance. So first, let's find the characteristic function. That is Laplace transform. But for the characteristic function, by the definition, that's the expectation e to the minus j omega x. And then consider all possible outcome, function of outcome, times the weighting, the PDF, the Laplace PDF, alpha divided by 2, e to the minus alpha times the absolute value of x dx. So here, because I have an absolute value x, if I take the absolute out, I have two parts. The integration from minus infinity to 0 and also 0 to infinity. So I have alpha divided by 2. First, let's see minus infinity to 0. I have e to the alpha minus j omega x dx. And then 0 to infinity, e to the minus alpha plus j omega x dx. This is alpha divided by 2. The first one, I have e to the alpha minus j omega x divided by alpha minus j omega. And then that x from minus infinity to 0. And the second term, e to the minus alpha plus j omega x divided by minus alpha plus j omega. And also x is from 0 to infinity. So you have alpha divided by 2. And here is 1 over alpha minus j omega plus 1 divided by alpha plus j omega. So you get alpha squared divided by alpha squared plus omega squared. Okay, that is the characteristic function. Next, how about the expectation? Well, for the expectation, we can just find it directly, or we can use the moment theory. So let's use the moment theory to find the expectation, and you can verify it by using our definition. Okay, so consider all possible outcomes times your weightings. But here, if I use the moment theory of D, take the derivative of your characteristic function and then set j omega to 0. It's d j omega. And we just found the characteristic function alpha squared times alpha squared plus omega squared to the minus 1. And then set j omega to 0. Still in the same line, we have minus alpha squared times alpha squared minus j omega squared to the minus 2 times the chain rule minus j to omega, and set j omega goes to 0. Set j omega equals 0, then you get 0. Now, to find the I need to find the variance, so I need the second moment. So to get the second moment, then I will get to take the derivative again, d squared of your characteristic function of x. Still, after taking the derivation, set j omega to 0. Eight alpha squared j omega squared divided by alpha squared minus j omega squared over O to the power 3. Two alpha squared divided by alpha squared minus j omega squared to the power 2. And then that j omega be 0. Then you'll get 0 plus 2 over alpha squared. So your variance will be the second moment minus the first moment squared. That is 2 over alpha squared. Next, very practical. A failed coin is tossed n times. And now I said this n is Poisson distribution with a parameter lambda. And I have an m. This m is the number of times that head occurs. Okay, then I need to find the PMF of m. So you see that m is the number of times head occurs. But how many times do I toss? It's not fixed. It's not like doing this 10 times or 20 times. How many heads do we have? Now this n also changes. So how do we find the PMF? Again, that since we know we can find the PDF or PMF by taking the derivative of your CDF, or you can find the characteristic function and then take the inverse Fourier transform. So we can, let's find the characteristic function of m. And then we take the inverse Fourier transform, we can get the PMF. So the definition, that's expectation e to the minus j omega m. So now, how do I know m? 3 times or 2 times? We should fix n first, right? So suppose I toss a coin 20 times, then I will see how many numbers of head occurs. Or I fix n for 10 times, then I will see the number of times that head occurs for m. So 10 times, tossing the coin 10 times, and I see maybe 3 heads occurs. And I fix 20 times, then I see 15 times of heads that occurs. So in this case, I have 2 random variables, but I think I should fix one. Then I can find the m using the total probability expectation. Total expectation. Let's fix n first. So suppose the random variable n is a number n. Then we need to times the PMF of n, which is Poisson. Okay, and this n is from 0 to infinity, because Poisson is from 0 to infinity. Okay, so that means I need to consider that when n equals 1, okay, then how many times of head we have? Now, when n equals 2, if I toss 2 times, how many times I get head? If I toss 3 times, how many times I get heads? So in this case, we know this is a Poisson. So that's me right here. Poisson, so e to the minus lambda to the lambda to the n divided by n factorial. And then we have the expectation, conditional expectation. So if I fix n, what is the distribution of m? If I fix n, for example, that n is 10, so doing this 10 times, then I got how many heads we have. So if I fix n, so doing this 10 times, tossing, then I get 5 heads, or I get 6 heads. And this number of times heads that occurs is a binomial random variable, right? Not just m is a binomial. I mean m conditioned on my n. If I fix my n, this is binomial distribution. Okay. So now for the n is fixed, we know in this case the m is binomial. Binomial distributed. Okay, so here m condition on n, this is binomial. And for binomial, my parameter is nm. So we can write it on the PMF. M over conditional on n. So that is n choose m. 1/2, because I toss a fair coin, so 1/2 to the m, and then 1/2 to the m minus m. So it should be 1/2 to the n. And my m is 0, 1, 2. The maxima is n. Okay. So knowing that, then we can bring it to here, because the expectation, remember, consider all possible functions of outcomes times their corresponding weightings. Here the corresponding weighting is this conditional PMF. Therefore, the expectation is the m from 0 to n consider all possible outcome times the weighting. So we combine these two. So we have 1/2 e to the minus j omega to the m, and 1/2 m minus m. That gives you 1/2 to the n e to the minus j omega n plus omega plus 1 to the power n. Remember, we haven't finished yet. We only did this part. Okay, so we'll bring it back to this summation. So we still have the summation we need to simplify. So thus, it follows for my characteristic function of m, that's summation n from 0 to infinity e to the minus lambda times lambda to the n divided by n factorial times the conditional expectation. This is e to the minus lambda e to the minus lambda times the summation n from 0 to infinity. So here we have lambda divided by 2 times e to the minus j omega plus 1 overall to the power n divided by n factorial. That's e to the minus lambda e to the lambda over 2 times e to the minus j omega plus 1. So you get e to the lambda over 2 times e to the minus j omega minus 1. So what is this characteristic function? If you check the table, you can see that this is a Poisson distribution or Poisson characteristic function. So Poisson with the mean lambda over 2, because the Poisson characteristic function is e to the lambda times e to the minus j omega plus 1. So we can write it down the PMF. It is Poisson, so PMF is lambda over 2 to the power m times e to the minus lambda over 2 divided by m factorial. And m is from 0, 1, 2 to infinity. Okay. Then you may ask, how do I know that for this kind of a question that I need to use a characteristic function to find the PMF? By experience. You can find the PMF directly. If you want to find the PMF directly, how do we find that? PMF, we know that's the probability. Okay, so it is a probability of m equals certain number. So here's m. But we still don't know the m. We know that if we fixed the n, how many tossing we have, then that is binomial. So we can do the total probability law. Summation n from 0 to infinity. If I fixed n, okay, here condition on n equals certain value n, then I need to times the probability of your random variable n fixed. Then this will be n from 0 to m. N choose m. 1 over 2 to the n m. And 1 over 2 to the n minus m. Times the Poisson PMF e to the minus lambda times lambda to the n divided by n factorial. I think in our homework we also have these similar questions that you can practice. Next, let's talk about the joint characteristic functions. If I have two random variables, I have a joint characteristic function, and which is defined here. And still the expectation, now I have exponential to the minus I omega 1 for x and omega 2 for y, and we do the combination. We know that the characteristic function is the Fourier transform of our PDF. So if I have a joint PDF, then our characteristic function, just taking the Fourier transform. Okay, and this one will be the 2D Fourier transform. So here, 2D Fourier transform. Then how do I get the joint PDF? If I have a joint characteristic function, so that is the inverse to the Fourier transform, we can get the joint PDF. So it will be 1 over 2 pi squared times the integration for R2, okay, e to the I omega 1 x plus omega 2 y times the joint characteristic function omega 1 and omega 2 d omega 1 and d omega 2. If y is the omega 2 is 0, what happens to this joint characteristic function? That is the expectation e to the minus, did I use I or J? I use I. Wow. I omega x plus 0 times y. Then I have expectation e to the minus I omega x. And what is this expectation? The characteristic function of x. You can put like a j omega, or sometimes you just put the omega. Okay, so similarly, if my omega 1 is 0, so I have a 0 omega, then that is the characteristic function of y. So if I have a random variable z, that is the linear combination of x and y, so ax plus by, then what is the characteristic function of z? So characteristic function of z v e to the minus I omega z. So z is ax plus by, so we can replace it by ax plus by. So here you have e to the minus I a omega x minus I b omega y. So it should be a omega and b omega. Okay, now let's see a theory. If x and y are independent, statistically independent, that means the joint characteristic function is the multiplication of their individual characteristic functions. So if and only if, how do I prove that? Let's prove, we need to prove it in both ways. So first, let's prove in the forward way. If x and y are independent, then we can write this equation. So first assume x and y are independent. Independent, that means the joint PDF is the multiplication of their marginal PDF. And also e to the minus I omega 1 x plus omega 2 y is e to the minus I omega 1 x times e to the minus I omega 2 y. So the joint characteristic function omega 1, omega 2, that's the expectation, e to the minus I omega 1 x plus omega 2 y. That's expectation I omega 1 x times the expectation e to the minus I omega 2 y. So that's why that's the multiplication of your each characteristic function. The other way, if we know this equation, then we need to prove x and y are independent. So assume the joint characteristic function can be expressed as the multiplication of two individual characteristic functions of x and y. Then using the inverse Fourier transform, the inverse Fourier transform the joint PDF. And that means if we can prove that the joint PDF is the multiplication of their individual marginal PDF, that means x and y are independent. So that will be 1 over 2 pi overall square. Integration to a real line e to the I omega 1 x plus I omega 2 y times the joint characteristic function. But since we know that the joint characteristic function can be expressed as their multiplication of each characteristic function. So here we can just plug in x omega 1 d omega 1 and d omega 2. So I can separate that too. First, I have a 1 over 2 pi for omega 1 e to the I omega 1 x times the characteristic function of x. And then the other one, 1 over 2 pi for y or omega 2. So e to the I omega 2y times the characteristic function of 2. D omega 1. Here. And then plus, no, not plus, times. So times this d omega 2. Then here we have f of x, the PDF of x, times PDF of y. So they are independent. The next theory, convolution theory. X and y are two independent, statistically independent random variables, and z equals x plus y. We know that the PDF of z, there will be the convolution of x and y. But here for the characteristic function, there will be also the multiplication of your characteristic function. Because for the characteristic function of z, we know that is the expectation e to the minus I omega z. So it is e to the minus I omega x plus y. And then since they are independent, so that's expectation e to the minus I omega x, and then expectation e to the minus I omega y. And this is just the characteristic function of x and characteristic function of y. So now overall, let's have make a not the table, but kind of like a review. So now if I say that x and y are independent, what does that mean? X and y are independent. X, y are independent, that means the joint PDF will be the multiplication of each marginal PDF. Similarly, the CDF, the joint CDF, will also be the multiplication of their individual CDF. Then the expectation of x, y, since they are independent, there will be the expected mean x and times the mean y. Oh, we just talked about the continuous case. Here for the PMF, joint PMF, similarly, the joint PMF, there'll be the multiplication of the marginal PMF. And then finally, the joint characteristic function will be the multiplication of each characteristic function.